So welcome back to the online seminar series, Machine Learning Needs Mathematical Optimization. So today we have the pleasure of having a presentation given by two academics, very good friends. So we have Juan Miguel Morales and Salvador Pineda. So they work at the intersection between analytics, machine learning, and optimization and energy. So I will tell you a little bit about both of them, and then I will give the floor to them. So Juan Miguel Morales, our first speaker, he's an associate professor at the Universidad of Málaga. So he did his undergraduate studies in Málaga, moved to Castilla-La Mancha to the university to do a PhD there in the group of Antonio Conejo. His postdoctoral studies are in Denmark, and then he took several positions at the Denmark Technical University. And finally, he got up to the associate professor position. He received an ERC grant and a starting grant in 2016, and then he moved back to Universidad de Málaga. So it's a nice cycle. Salvador Pineda is associate professor at the Universidad de Málaga, did his undergraduate studies at Universidad de Málaga, moved to Castilla-La Mancha, also to the group of Antonio Conejo, did his PhD there, took some postdoctoral studies in Denmark, and then finally he had an associate professor position at Copenhagen University. And in 2016, he also moved back to Universidad de Málaga. We are very pleased having them here. The talk today is about uncertainty, and we are looking forward to hear what you have to say on this. Thank you so much.
Thank you very much, Dolores, for your nice introduction. I would like to, Salva and I would like to thank Dolores and Emilio for giving us the opportunity to participate in this interesting seminar series. As Loli said, the title of our talk is Contextual Decision Making Under Uncertainty. And this is a joint work with our PhD students, Miguel Ángel Muñoz and Adrián Esteban Pérez. Before starting with the subject matter of this presentation itself, I would like to introduce a little bit ourselves. Both Salva and I are professors at the University of Málaga, as Loli said, which is an important university located in the south of Spain, in a beautiful city located at the Costa del Sol, Málaga, where it is actually very difficult to see the rain. They say, and hopefully it will be true, that Málaga is becoming the Silicon Valley of the south of Spain. And actually, Google has recently decided to open a cybersecurity center of excellence here in Málaga. Our research group is called OASIS, Optimization Analytics for Sustainable Energy System. It was established in 2018. It is a small group of young researchers who essentially like optimization, statistics, and smart energy grids. You have here, in case that you are interested, the link to the website of our group, this oasis.uma.es. Okay, so after this short introduction, let's now talk about the science. The focus of this presentation, I think you can see the pointer, the focus of this presentation is the following conditional stochastic program. The idea is that we want to find a decision X within a feasible set, capital X, such that the expectation of the cost function F is minimized given, and this is what makes the stochastic problem conditional, given that some auxiliary information is available to the decision maker. We take the expectation of the cost function because we see that it is affected by some uncertainty, which we denote with the random vector Y. The site information, the auxiliary information is modeled by another random vector set that we believe that has some predictive power on the uncertainty Y, and that has taken the value set equal to set 0, sub 0. Q here, over which we take the expectation, is the joint distribution of set and Y, whereas this Q sub tilde chi is the conditional distribution of y given set equal to set 0. So both formulations of the very same problem are equivalent. Okay, an example of a conditional stochastic problem, which is maybe a bit silly, but I think it illustrates very well what that problem conveys. Suppose that we are running an ice cream shop, and that at 10 a.m. in the morning, we need to decide how much ice cream we're going to produce. This is our decision X. At 10 a.m., however, we don't know the demand for ice cream in the afternoon, but we can use some available information, which we typically refer to as the context. For instance, the context could be the temperature at 10 a.m. in the morning. To make we want to exploit this available information about the temperature to make a better decision. Why? Because we know that there is a strong relationship between the morning temperature, our variable set, the context, and the ice cream in the afternoon, our uncertainty y. We would like to exploit the relationship between the temperature and the demand for ice cream, between the set and the y, to make a better decision x. So this is just a very small example of what a conditional stochastic program. Okay, so we want to solve the conditional stochastic problem that we have seen before. However, we are faced with a fundamental challenge. Neither the true joint distribution that is generating the data, the pairs y and z, nor the conditional distribution are known. So the only thing that we have at our disposal is a data sample of size t of the joint distribution, which we denote with this pair set t yt. So what do we do? Here you have some possible solution approaches, all of which are based on building surrogate or approximate models, because we don't have, as I said before, the true joint distribution of the data or the conditional distribution. The first one is what we call the classical or traditional forecasting approach. We use the data that we have to infer the expectation of y given set equal to set 0. We then plug this expectation into the minimization, and we pray for this new surrogate minimization model here to be as close as possible, to provide a solution as close as possible to the one we want to actually solve, which is this one, the conditional stochastic program. However, we know that this approach is essentially wrong because it ignores the uncertainty and therefore its impact on the cost function f. As an alternative, we can try to learn a rule mapping the context directly into the decision x, in the hope that this mapping rule here is as close as possible to the solution of the original problem. The main problem with this approach is that we need to guarantee that the decision given by this mapping rule is feasible. That is always in capital X, the feasible region of the smaller x. There is a third approach that is similar to the traditional one. The idea is very similar. Basically, what we want to do is to use the data to compute a mapping rule here from the context to the uncertainty y, possibly very different from the mapping of the expectation of y given set, such that the resulting deterministic problem is indeed closer to the original one, and closer in terms of their solutions than if we had just replaced this here with the expectation of y given set equal to set 0. And the last approach that we are going to discuss today in this presentation consists in using the data to get a proxy of the conditional distribution. Unfortunately, it seems that the white hat has appears displaced from the Q distribution. So the idea is to get an approximation of the conditional distribution of y given set equal to 0, which we denote with this white hat Q, sub she tilde, and then solve this surrogate model instead. In all cases, the only thing that we have, and I insist, is the sample data from the true joint distribution, right? So we need to either create the mapping rules that we have seen before, or this approximate conditional distribution from this data sample. All these solution approaches are discussed in these two papers of ours, whose preprints are currently available through arXiv. And now Salva is going to take the lead, and he's going to talk about the three first approaches that I have briefly summarized before. So Salva, you can take the lead now of the presentation.
Okay, thank you, Juanmi. So as Juanmi said, I'm going to explain you a little bit more about the parametric approach that we discussed in this paper, and this is part of the PhD of Miguel Ángel Muñoz, who is listening, I hope. Just to correct if I say something silly. The three approaches we are going to discuss, as Juanmi said, is a forecasting approach, the decision rule approach, and the bi-level approach. Juanmi, I think you can mute yourself, maybe. So the first approach is going to try to learn the relationship between the uncertain parameters y. How do I point here? Do you see my mouse? So we are going to learn the relationship between the uncertain parameter y and the contextual information set. But the whole point is that we are going to ignore completely the objective function and the feasible set of the optimization problem we are solving. In the second approach, we are going to learn the relationship between the optimal decision x star and this contextual information. And in the third one, that is actually the one we propose in this paper, we are also going to learn the relationship between y and z, as in the first approach. But in this case, we are going to take into account the objective function and the feasible set. So let's see how this is done. Yes. So you can find all this. This work has a lot of notation, and I wanted just to simplify it a little bit. So I'm going to start with actually an application that we use to show how our method works. And this is the problem of a strategic producer. We usually apply to energy producer, but you can think of any kind of producer like, I don't know, tomato producer or anything, where you have some inverse demand function that is going to relate the prices and the demand, and then you have some cost. So basically, you have to decide how much the quantity you are going to produce to maximize profit. And under some typical assumptions, you end up with this kind of quadratic optimization problem, with your x being your decision variable and this y being your uncertain parameter. And then your decision variable is bounding between x bar and x upper bar. So this is quite straightforward to solve if you think about it. So if you take the first derivative of the objective function, you can see that the minimum of this quadratic function is at y divided by 2. So if this value is between the bounds of my decision variable, then that's the optimal solution. If this value is on the left-hand side, then we have the decision is to produce the minimum quantity. If it's to the right, then we have to produce the maximum quantity. As you can see, it's a little bit easy to see, but it serves us very well to show how the method works. Yeah, so this is just some numbers on this example. So we have just 4 time periods. This set is our contextual information. You can think of it as the temperature, as Juanmi said before. And this y is actually the uncertain parameter. and I just put half of y, because if this value is between 0 and 1, that are my bounds of my decision, then that's going to be my optimal decision. If this value is above 1, then my decision is just exactly 1, because you cannot produce more than 1, just for illustration. On the left-hand plot, where I presented is the uncertain parameter as a function of the contextual information. And on the right-hand plot, you can see the optimal decision as a function also on the contextual information. So you can see that if this uncertain parameter is above 2, then the optimal decision is just x equal to 1. Otherwise, it's just half of this value. If in this case, so the decisions on this plot on the right are made assuming that you don't have any uncertainty, right? As if you have a crystal ball and you know exactly the values of y. In that case, the income you would get is 21.1, and this is like our benchmark, right? Because in reality you don't know this uncertain parameter y, then probably due to this lack of information, you are going to also decrease this income. So the whole point of my presentation is comparing how much we are losing for each of these three methods. So in the first method, yeah, what we're going to do is assume that we have a linear relationship between the uncertain parameter and the contextual information set. And this is why these methods are parametric, because I assume a family of functions, which in this case is the family of linear functions. They are for simplicity and illustration. And then I have two parameters that I need to adjust, and this is A and B. Then how do I estimate A and B? I guess we all know this. You can use minimum square errors to adjust the parameter of this basic linear regression. And once these are adjusted, if a new time period comes, then you estimate the value of your uncertain parameter y hat using the values of A and B that we have determined in the previous step. And about your decision, you just take this forecast value for your uncertain parameter, and then you solve this optimization problem. This is what it has been done for several years, and it feels very natural. You have some uncertain parameter, you adjust some learning method, and then you forecast for the new time period, and then you decide. In this example, we adjust on the left, we have adjusted these 4 data points to a linear function. And these here are the errors. And the root mean square error is 0.6. The blue points are the estimations for each of these data points. So, and then for each of these blue points, we have to make a decision. So as you can see now, these two points here, which are above 2, the predictions go below 2, so the decision is actually changed a little bit. So your decisions on the right-hand side are quite close, more or less, to the optimal one. So the one we got with the crystal ball that are in black, but not exactly the same. So at the end of the day, we are losing the income we get is 95% of that we got in the benchmark. So we are basically losing like 5% of income. This is the first more like traditional approach. In the second approach, we say, okay, let's forget about the uncertain parameter y, and I'm going to just learn the relationship between the optimal decision x star and the contextual information set. And I'm also going to do that assuming a linear function, just for the sake of comparison. So what I do to estimate this A and B, well, as you can see, it's still a parametric approach. How do I estimate this A and B? I just solve this optimization problem. It's the same as before, but now we minimize the summation over all data points that I have in the training set. But the different thing is that now I have imposed that my decision has necessarily to have a linear relationship with the contextual information set. Then once these A and B are adjusted, if a new time period comes, I can just plug the value of the contextual information in this linear function, and then I get my optimal decision. So this is very straightforward, because for new time periods, you don't have to solve an optimization problem. You already got you already get your optimal decision by evaluating like a function. For our data, now this is the optimal decisions with as a function of the contextual information. This is the best linear function that approximates these two things. Well, I guess someone is saying, well, this approximation is not very good, because for this data point here on the left, the error is quite high. And the problem is that you have to ensure that your decision, it stays between 0 and 1, because that's the bounds on your decision. So that's why it looks a little bit like not very well approximated, but that's the reason. If you do this, you also lose some money due to this approximation, and this is it's more or less similar to the previous one. It's around like 5% losses. But there is another important thing about this method, and is that if a new time period comes, for example, at the value of set is here to the right, you may even get like infeasible solutions, because your optimal decision would be above 1, and that's infeasible. So there is that's another very important drawback of this second method. And now the third method is the one we are actually proposing in this work. And our proposal is based on bilevel optimization. So I'm not sure if everybody is familiar with bilevel optimization, but in case you're not, I have here like a very simple example to illustrate what bilevel optimization is about. So it's about two friends, John and Peter, and they go every week to the movies. That was before COVID, I guess. And so the way they have to decide the movie they are going to watch every week is first, John decides the movie theater, and then Peter decides the movie within that movie theater that John has chosen. So that's kind of the game they have. So first, John decides the theater, and then Peter the movie. So they have their preferences, of course. John prefers action movies over terror movies. He doesn't like very much romantic movies. Peter is kind of the other way around. So his favorites are romantic movies, and he doesn't like action movies very much. So given this game and there are two theaters available. Theater 1 is Spider-Man Notting Hill, and Theater B is The Exorcist and The Matrix. So maybe you can think about 5 seconds the theater that John would choose, considering like his preferences. So it's not that difficult to see, I guess. So let's imagine that John chooses theater A. Then Peter is going to come and choose Notting Hill, that is a romantic movie, and then John is going to be a little bit pissed off, because that's the movie he doesn't like at all. So the right answer is that John is going to choose theater B, because there is no romantic movie theater, and then at least he's going to see like the terror movies, right? So this is I don't know if I succeed to show that this is like a sequential game. So first John decides something, and then Peter decides another thing. So there is a sequence of decisions, and then this is non-cooperative because each of them, they have their own preferences about movies. So somehow what John is doing is anticipating what Peter is going to do to make his own decision. And this is more or less what bi-level programming is about. In a mathematical notation, this is how bi-level programs are formulated, where you have basically one optimization problem inside another optimization problem. So this is the upper level and the lower level. And the key thing here is that the upper level problem is somehow anticipating what is going to happen in the second level, the same as with John and Peter. So going back to the method we propose to make decisions, we are going to assume as well a linear relationship as in the first method between the uncertain parameter y and our contextual information set. But now A and B are not going to be determined using minimum square error regression, but we are going to compute them solving this bi-level optimization problem. So what we are doing here is deciding A and B, anticipating that these two parameters are going to use in an optimization problem with a given objective function and a given feasible region, right? So while in the mean square errors, you are just hoping to minimize the forecast error, here you are just taking into account the optimization problem you are actually solving. Once these two parameters are chosen, if a new time period comes, then you plug the contextual information in, and then you solve the same optimization problem as before. So this looks, the next question is, okay, so how do we solve this bi-level problem? Under some convexity assumption of the lower level, what most people do is just to replace the lower level by the KKT optimality conditions, and then you get just a single level optimization problem that is a little bit difficult to solve because it's non-linear, because you have products of dual variables and primal variables. It also doesn't satisfy some constraint qualifications, so it's not that easy to solve, but there are some strategies. This is very well known in the literature. One of them is to replace the complementarity conditions using binary variables and large enough constants. This solves a little bit the problem, but partially because you need one binary variable per data point. So you have a lot of data, you are going to be in trouble. And also, adjusting these big ends is not an easy task. So another alternative is using the regularization method, that instead of imposing that the product of dual variable constraint has to be equal to 0, we'll relax it a little bit with parameter epsilon that is iteratively reduced. This is quite fast, and it works relatively well to solve linear bi-level optimization problems. So this is the solution. So as you can see here at the top, we have also a linear relationship between y and z, but now it's a little bit funny, because here with the point at the right, you have a huge error. Indeed, the root mean square error is now 0.75. If you remember from in the first case, it was equal to 0.6 or something like that. So we have increased our error, right? But now, if you will look at the decisions induced by these three blue points, we get that they are almost equal to those provided in the benchmark. So actually, for these 3 points here, they are exactly the same. That's why you only see the blue one. And here in the right, we have a small error in the decision. and the income losses that we have in this case is only 0.1%. So we are losing around 5% in the other two cases, and only 0.1 in this case in the method we propose. So next question is, well, you can always find an illustrative example where things work as you want them to work. But sorry, this is just a small comparison of the illustrative example. This is what I was saying before. So we see an increase in the root mean square error of the uncertain parameter, but the income is significantly improved. So we've also tried in a more realistic case study. To do that, we use data from the Iberian electricity market to approximate the inverse demand functions. So we apply it to electricity producers. We use as contextual information, we use wind and solar power forecasts. And we did it for 3 different generation technologies, base technology that basically means it's always on, like nuclear, medium, like carbon, and peak. So this is only on when you have very high demand, like gas technology. And to compute the average result, we run it in different data sets of 200 hours. And we use 160 for training and 40 as test sets. And this is the results we got. So the first interesting thing is that if you have a base unit like a nuclear unit, uncertainty about the market is not very important, because basically you're going to be always on and running. So that's why the 3 methods provide very similar results. However, this is not the case for the medium and the peak. So depending on the market conditions, you will be maybe running up to your maximum production, or you'll be like midway, or you'll be not producing at all. So this uncertainty has a lot of impact. And this is these numbers here are the relative incomes. So you can see, for example, for the medium unit, we got 3% higher profit, and for the case of the peak unit, we got almost 20% more profit. And also in the last row, I included, if you remember, in the second approach, in the decision rule approach, where you just relate the optimal decisions with the contextual information, to have the risk that your decision is infeasible, and that actually happened in a non-negligible number of cases in our case study. So you have to be careful with this type of approach. As a summary of the parametric approach I talked to you about, we have the forecasting approach, learning the relationship between Y and Z. This is interesting because you have a wide variety of methods. We just use linear regression, but you have like random forest, decision trees, etc. The problem is that your decisions are going to be suboptimal, because you're basically ignoring the optimization problem you will have to solve. Then in the second approach, we found the relationship between optimal decision and contextual information. The good point is that you can decide very quickly the decision, but the problem is that that decision can be infeasible. And then in the approach we propose, the bilevel approach, we are learning the relationship between Y and Z, but taking into account the optimization problem, and this is going to provide much better decision. The problem is that you have to solve the bilevel problem. So in our case, that was a quadratic problem with linear regression. It's not that hard, but further research is required to apply this method to other problems. So I think I'm going to stop here and pass it to Juan, who is going to talk to you a little bit more about the non-parametric approach.
Okay, thank you, Salva. So recall that the last solution approach that we were going to discuss in this presentation is the one that I have highlighted here in red, and is based on getting a proxy of the conditional distribution of the uncertainty given the context from the available data sample. I guess that you will all agree with me if I say that in principle, the empirical joint distribution of the data is the best proxy we can have of the true joint distribution that generates the data. Okay, so the problem here is that we need a proxy of the conditional distribution, not a proxy of the joint distribution. And this is where all the challenge is going to rest on. The most straightforward way to get such a proxy is then to somehow fabricate it from the joint empirical distribution of the data that we have in this figure, right? The blue points represent the joint empirical distribution of the data. So this is what we are going to do here. We have a direct distribution supported on each of the blue points, which we somehow, and this somehow is key, we're going to weight as a function of the context with this W here to build this conditional empirical distribution that we're going to use as a proxy of the true one. Then we can plug this empirical conditional distribution into the minimization problem that we have seen before and get the following surrogate model. This surrogate model here. Okay, this is actually what they propose in this recent paper that I have indicated here by Bersimas and Kalus. One of the advantages, of the clear advantages of this approach is that the resultant surrogate model is tractable in the sense that the expectation only needs a t evaluation of the const function for a given decision x. But the problem is, how do we go from the joint empirical distribution of the data to the conditional empirical one? And this is the crux of the matter, because this question somehow is telling us that, in fact, there are potentially many ways to do so. There is ambiguity about how to construct the conditional empirical distribution from the joint data. For example, we can use k nearest neighbors, and when we wonder which value of k we need to use, or we can use Nadaraya-Watson kernel regression, and then we need to wonder which kernel we are going to use, etc. Here we have an example when we use two nearest neighbors. Basically, we take the data points that are closest to the context, and these two data points constitute the proxy of the conditional distribution we are looking for. Based on this proxy of the conditional distribution, we can solve this deterministic minimization problem. Of course, this doesn't work well because we have this previous method here does not work well, because especially when we have a small sample size, because the surrogate model is going to be very optimistic and will suffer from what we call the curse of the optimizer. Essentially, and I insist, this is so because there are many ways to build the conditional empirical distribution. For this reason, in another recent paper by Bersiman, McCord and Stewart, they propose to minimize over the worst case conditional empirical distribution that may result from moving the data points within a certain distance from the original locations given by the local predictive methods, in this case given by the two nearest neighbors. This epsilon t is precisely the distance that we can move these 2 points apart. In fact, they go a little bit farther and consider the worst case distribution within a Wassertian bulb of radius rho that is centered on the conditional empirical distribution given by the local predictive methods. Okay, so they consider all the probability distributions that are within a distance rho from the conditional empirical distribution that we have built using the two nearest neighbor, for example, method that I have put as an example before. For those of you who are not very familiar with the Wassertian distance, let me just say that it is a metric to measure how different two distributions are, and that can be actually expressed itself as a minimization problem, what we call an optimal mass transportation problem. However, the truth is that Bersimas et al. Do not fix the key problem, which is that there are many possible conditional empirical distributions we can build from the joint data sample. So what we propose instead is to use an ambiguous center for the Wassertian ball. This ambiguous center here is given by the 1 minus alpha trimmings of the joint empirical distribution of the data. And it is made up of all distributions supported in at most t points, each with a maximum weight given by 1 divided by t multiplied by alpha. This way, we don't have to stick to a particular empirical conditional distribution, but we are considering all possible ones at once. This is very interesting, actually, because this way we can protect our decision against the inference process made by the local predictive method. For example, think of the two nearest neighbors. It could be that the third neighbor is almost as close to the context as the second one, but its impact on the cost function is by far more harmful in terms of the cost. Okay. In the end, we need to solve this distributional robust optimization problem, where this constraint that you can see here, this constraint 2b, is a partial mass transportation problem, and alpha of the trimming set, this alpha t, is the minimum amount of data points from the joint empirical distribution that must participate in the construction of the conditional empirical distribution. This row here is the budget, the degree of the transportation budget, the degree of robustness. The higher the value of rho, the more conservative our decision will be. Okay, in this slide, I'm just summarizing very quickly the good things about our approach. First of all, it is as tractable as the other approaches that are based on distributional robust optimization. And we can also prove that it features nice performance guarantees under mild assumptions. Performance guarantees in terms of convergence, consistency, and finite sample guarantees. Here, it is an example to illustrate the different methods for approximating the conditional distribution we have seen. There are more examples in the paper. This deals with the popular single-eaten use vendor problem, where the uncertainty, y, represents the demand for a product. In our case, it could be, for example, demand for ice cream. And the context may represent the outside temperature for the ice cream example. We have h as the unit holding cost in case we need to store some of the ice cream that we have not sold, and the back order unit cost represented the cost of not satisfying the demand. This is the conditional stochastic problem we decided to solve, which is known to be equivalent to a conditional quantized regression problem. These are the methods, the three methods proposed by Bersimas et al. That I have just talked about before. Our method is denoted as DRO trim from trimming sets. Okay, so let's see some results quickly. Okay, here on the left plot, we represent the true joint distribution together with the true conditional distribution given by the context here. On the right plot, we represent the optimal solution given by the different methods as a function of the sample size t. These optimal solutions depend on the data sample, and therefore we provide its expectation, which are the solid lines, okay, and the 15 and 85 percentiles. The dotted line that you can see here represents the ideal solution. That is the solution we would get if we had full information, if we solved the original conditional stochastic program. Just to say that our method, as you can see, our method not only provides solutions very close to the actual one, but also it's very important to see the variance of these solutions compared to the other methods. Okay, here on the right plot, we represent the actual expected cost that we achieve when the optimal solutions given by the different methods are implemented. Again, the dotted line here represent the expected cost with full information. Observe how our method substantially performs the other ones in expectation, but also, and very importantly, in terms of variance of the actual cost that we get for implementing the decision that it delivers. Lastly, here on the left plot, we represent what we call the auto-sample disappointment or regret. The auto-sample disappointment is basically defined as the difference between the actual cost of a decision and the cost estimated by the method from which we got that decision. Meaning that a positive regret is a bad surprise, while negative values mean a good surprise. Here, just to highlight that all the methods that are based on distribution robust optimization, our method DRIO-TRIM, the KNN robust method proposed by Bersimas, and the KN-DRIO method proposed also by Bersimas and all, they all are able to keep the auto-sample disappointment negative, that is to produce good surprises when we implement the decisions. But in our case, our method not only is able to keep the regret negative, but also to provide better performance in terms of actual expected cost. Okay, so just to finish, I think these are the conclusions of this last approach. We have built a distribution robust optimization approach based on optimal transport to solve the conditional stochastic optimization problem. We prove that tractability is preserved. There is no more tractability issues that those we have with the classical DRO methods. We also have performance guarantees in terms of we are able to ensure that when the sample size is large enough, we are going to get the optimal decision with full information and the optimal cost with full information under mile assumptions. And also we can see that the method has significant improvements over alternative approaches as well, presented in the literature. So I think that's all. These are the references that we have used. Thanks for your attention, and if you have any questions, both Salva and I will be very willing to reply to them.
Thank you, Juan Miguel, and thank you, Salvador. As usual, we open the floor for questions, and then you can unmute if you don't mind. Put your camera on. Vladimir, would you like to pose your questions?
Oh, okay. Can you hear me?
Yes, we can.
Okay. So let me just repeat what I just wrote. Thanks for the talk. It was very inspiring, and I'm very curious about your high-level frameworks that you presented in the first part of the talk. And I'm curious if you could comment on the statistical consistency of the predictions made by bi-level framework. So if you would use it like many times, would the predictions of the bi-level problem converge to the expected value of the uncertain parameter, or you actually produce some biases towards cost optimal decisions, right? And my second question is about the same bi-level framework, but I also think it can apply to this non-parametric approach for the second part of the talk. Can you deal with the cases when the uncertainty is contained in the feasible region of the problem? Thank you.
Salva, do you want to try to answer, or should I answer? Or?
So the second one, we haven't really tried with optimization problems in which the uncertainty affect the feasible region. So we were we did some experiments, and things started to get a bit nasty. And then we decided to first stay with uncertainty only affecting the objective function. So this is one of the assumptions we make in the preprint. And regarding the first one, I'm not sure.
Yeah, maybe I can answer that. Yeah. Vladimir, no, there will be a bias, because here, when our purpose, we don't want a method that converges to the expectation of Y given Z, given the context. We are not interested in that. Here, statistical consistency is measured in other terms. Here, we measure statistical consistency asking answering the question whether our bi-level approach is going to give the best possible decision with full information, if we have full information. So we say that our method will be consistent if when we have a large sample size, the decision that we make with our method will be the same as the one we will make with the full information problem. So we don't want consistency, we don't want to retrieve the actual expectation of Y given the context. I don't know if this answer, so we will have a bias, because maybe yeah, tell me.
Does it mean that this prediction that your bi-level model does is good for a decision maker, but it's not good for a general public?
Exactly. It's not general. It's not good for the optimization problem, which is the minimization of the square error. Is not good for that one. Is good for the optimization problem, which is having the highest benefit possible in the market.
Okay, thank you very much.
Thank you very much. We have a hand from Itamar. Would you like to?
Yeah, I was wondering how a flexible and clever consumer can enjoy your beautiful analysis to take advantage.
The consumer, what do you mean?
Well, you work in a project that focused about flexible consumers. So the question is, now that the analysis is more or less in good shape, suppose I am a flexible consumer and I read your analysis, how can I take advantage of it to save money or to be more efficient?
Yeah, the question more is like I mean, I can help you as far as you have some uncertain information affecting your decisions one way or another, and B, some contextual information that it may help you to reduce uncertainty. If you have these two things, then you could apply. I mean, you can always formulate the bi-level approach we propose. However, depending on how your objective function looks like and how your feasible region looks like, solving this bi-level problem may be more challenging than what we show here, which is a more stylized application.
So, are there some easy way to work out examples to optimize it from the point of view of the flexible consumer?
Well, I mean, if you formulate your consumer problem as a quadratic optimization problem, then you can just use it without anything else.
Okay, wonderful. Thank you so much. Good presentation.
Thank you very much. And Achilles, you pose a question in the chat. Would you like to unmute and?
Yeah.
Like
hi.
Yeah.
Can you hear me?
So much.
Oh, okay.
Yes, we can hear you very well. Yeah.
Well, thanks for the presentation. For the first method with the bi-level formulation, well, I guess the standard approach is to do a prediction and then optimizing the problem. Have you considered also, I mean, in your comparisons, the case when you use probabilistic prediction? So you have the conditional distribution, and then you optimize to find the solution, in comparison to your bi-level, which I assume is deterministic approach.
No, we haven't tried that, and the reason is that maybe we didn't. I don't know if I can go to slide one. The reason is that so the final point is that you can solve your optimization problem for a new period like in a fast, let's say, and quick manner. So you don't want, of course, you can go to more traditional approaches where you have like a lot of scenarios or even a distribution itself. But we wanted to solve it and to make decision in a fast way. I don't know if Juan wants to add something to that.
Oh, okay, thanks.
Thank you very much, Kilas. Is there any other question? So, David, yeah, if you could unmute, please. Thank you.
Yes. Can you hear me?
Yes, we can.
Yeah. Hi, Salva and Juan. Thank you for your presentation. Very nice presentation. So my question here is well, I'm trying to understand in your contextual bi-level problem. So basically, you are embedding this forecast fitting, and this could end up in some overestimation or underestimation of some particular key parameter of your optimization problem. Like, for example, in the news vendor problem, you can overestimate or underestimate the demand of the item. And basically, I think for me, it's clear, like, depending on the cost of, for this particular problem of the news vendor, if you are, if your cost of overstocking or understocking are different, so you can actually understand, like, it's better to underestimate or overestimate. But all of this is related with the risk of your forecast. How this is connected with the approaches that are embedding into the objective function some risk measurement related with these data points?
First observation, yeah. So you are aware of this. Using this approach in case where your objective function is linear, it's a little bit trickier because there is an incentive of the upper level problem to find multiple solutions in the lower level problem, and then you get kind of nothing. So you should solve your bi-level problem considering the pessimistic solution. That's not always an easy question. So that's the first thing. And the second one, you said if how this compared to considering risk in the objective function, I guess.
No, I'm trying to get some intuition of, because you have a linear regression as your forecast tool, and basically you estimate parameters of your linear regression, and this will try to overestimate or underestimate demand in the case that your Y is demand.
So if you, depending on the asymmetry of your cost in the news vendor problem, then this is going to capture that. So if for example underestimating your demand has no cost, then you are going to be biased to make prediction in the other direction, if that's what you're asking.
Yes, so that's right. So the output will be some forecast will be underestimating or overestimating, depending on the cost.
It would be like a quantile.
Yes.
Yeah. I mean, in the case, sorry, in the case of the news vendor problem that you have that you are mentioning, the idea is that you don't want to, I mean, your linear regression function, if we train it through the bilevel model, is going to converge to the quantile regression, because the Nussbaum problem, I mean, I put it here, but it's difficult to go to the end. I don't know how to. I mean, in the Nussbaum problem, basically what you are trying to do is to estimate a quantile. This quantile is based on the B and H, which are the asymmetry of the cost. So the bilevel problem will give you a linear function that is trying to capture that quantile specifically, while the traditional forecasting approach is trying to capture the expectation, and the expectation we know that is not the best is not the good solution for the Nussbaum problem, because the good solution for the Nussbaum problem is a specific quantile of your probability distribution. Mm-hmm. I don't know if
yeah, okay. No, yes, but this traditional forecast-based tool is risk neutral.
Yes.
Yeah. So yeah, my point was here is just if there is some connection of some
there is, yeah, there is, and I would say it's a different framework. You could also, as Aquila said, you could also have maybe you can use statistics. You estimate a proxy, as I said in the last part of the presentation. You estimate a proxy of the conditional distribution, what we have always called scenarios, based on a probabilistic model or whatever, or using KNN, whatever. And then you solve a stochastic problem with some conditions, with some risk measure. Okay, that's another approach. And actually that approach is essentially somehow you are estimating the conditional distribution that you are gonna have. If you have more risk, then this conditional distribution will be placed on the worst scenarios. Will give more weight to the worst case scenarios, right? So it's a different approach. Here, the idea of the bilevel approach is having something more clever than the traditional regression, for example, the traditional point forecast.
Mm-hmm. Right. Yeah. Thank you. Thank you for the presentation.
Thank you very much for the questions. I think we are going to leave it here for the sake of being on time. So we would all like to give a round of applause to Salva and Juan Miguel. And for the rest of the people, remember that we are taking a 2 weeks break, Easter break, and we will be back in April with the next round of presentations. Thank you very much for your attentions, and see you back in April.
Thank you.
Thank you.